All right. This is it. This is the Physics C mechanics free response questions. This is only one set. They don't have the other set, so if you had the other set, sorry, you're just gonna have to kind of live and not know what what the answers are to that set. This is for partially blind. I did kind of look at some of the stuff ahead of time to first off make sure I kind of knew what I was doing and not make myself look like an idiot on the internet, because that's probably about the worst thing that can happen to me at this moment. Okay, let's take a look at these problems. Okay, so question number one. Okay, two blocks, 1 and 2, they slide towards each other on a horizontal surface. Block 1 has mass m and slides in the positive x direction, constant speed 2v naught. Block 2 has mass 6m and slides in the negative x direction with constant speed v naught, as shown in figure 1. Blocks collide, stick together. Collision occurs from 0 to tc. After the collision, where t is greater than tc, the blocks move together with same constant speed. Okay, well, we can kind of figure because they stick together, right? When it makes sense if they change speed on each other. Diagrams in figure 2 can be used to represent the momentum of the blocks before and after collision. Momentum vector for block 1 is already shown. Draw arrows on the grids to represent the momentum vectors. Okay, so it wants you to draw the momentum vectors on block 2 before the collision, and then the two block system before and after the collision. So to draw each, by the way, each little line right here, kind of each like square is like one, basically like 1 MV, right? So block 1 is going to the right with 2 MV. Okay, and we know that because it's 2 times mv, right? The momentum is 2 mv naught, right? Well, block 2 is going in the negative direction with 6 mv naught, right? So we should see that block 2 is going to go, it should be going to the left 1, 2, 3, 4, 5, 6. Okay, so it should look something like kind of like that. Okay, and it should just go straight to the left. Okay, the two block system after the collision, sorry, before the collision. Actually, I think it's easier to solve it after the collision first. I'm going to just do some math really quickly. Do conservation of momentum. I know that block 1 initially has 2 mv naught, and then block 2, or sorry, block 1 has 2 mv naught. Block 2 initially has negative 6 mv naught, and I set that equal to the combined mass, which is 7 m times v final. And I then need to figure out what is the final velocity of the system going to be here. I might actually be kind of jumping the gun on solving this a little bit, but I think it's easiest to do that. So I'm going to do solve for v final, and all I have to do actually, and this is pretty easy, is just take out my m's, and I should get 2v naught minus 6v naught. That gives me negative 4v naught on the left side. Negative 4v naught on the left side equals 7v final. And then v final is just going to be, what is it? Negative 4 over 7 v naught. Okay? Negative 4 over 7 v naught. Okay? So the final momentum of the system, right? The final momentum of the system, I'm going to say P final, is really just equal to 7m times negative 4 over 7 v naught. And then you'll notice that your 7's cancel out, and you get negative 4 mv naught. So our arrow should have a magnitude of 4 to the left after the collision, right, from the starting point. 1, 2, 3, 4. Okay. And by conservation, and remember, in all collisions, momentum is conserved, so your momentum after the collision needs to be the same as momentum before the collision. Okay. So 1, 2, 3, 4. Okay. So these two diagrams should actually be near identical to each other. Okay. Okay. During the time interval between 0 and tc, if force F is exerted, there's our force function right there. A is a positive constant, F max is the magnitude of the maximum force exerted on block 2 by block 1 during the collision. Derive an expression for F max expressed in terms of M, V naught, A, and TC, and then physical constants. Okay. I'm going to do this on a separate sheet of paper because it is going to be kind of a lengthy derivation to solve through. So I'm going to do this on a separate sheet of paper here. College Board would probably not like that. They would probably make me file an irregularity report if they saw me doing this. Okay, so just to kind of hit you with some real quick facts that we already went over. My final velocity was -4/7 v naught, right? And my immediate thought process is there's a relationship between this force function and not momentum, but the change in momentum, and that's impulse, right? And I did print out my formula sheet here so that I could refer to it. And I actually didn't really refer to this very often when I was kind of looking at them. This right here is our impulse. Our impulse is the integral of the force function with respect to time is equal to the change in momentum. And we integrate from our initial time to our final time. Our initial time is going to be 0. Our final time is going to be t sub c, right? So I'm going to that's exactly what I'm going to do. I'm just going to calculate that out, okay? I use a different color here. That's my final velocity. If I find out, and you can solve this. I think you can solve it for either block, and it works out just fine. I'm actually going to do it with block 2 because that was in my head how it worked out best is use block 2 because that's where the force is being exerted on block 2, right? Now technically the force is being exerted the same on both of them because Newton's third law, but I'm just doing it with respect to block 2. So I can say that the change in momentum for block 2 is going to be equal to its final momentum minus its initial, right? Well, its mass doesn't change. Block 2, if I'm not mistaken, is the 6m block, right? Yeah, 6m. Okay, so then the final momentum for block 2 is going to be 6m times that velocity. So 6m times -4/7 v naught minus my initial momentum, which is going to be, again, still 6m times, and then my velocity is negative v naught in the, is v naught in the negative direction, right? So it becomes negative. And the first thing I notice is I can actually factor out my I almost call them GMs. There's 6m's, right? So it's going to be 6m parentheses -4/7 v naught minus negative v naught. Okay. Oh, minus negative v naught, that's just going to turn into positive, right? Okay, plus v naught, right? Okay. And when I do this, right, -4/7 v naught plus 1 v naught is going to give you 3/7 v naught, right? So this becomes 6m times 3/7 v naught, and then I multiply the 6, and this becomes 18/7 m v naught. Okay. So this is my change in momentum. This is half the problem, right? That's just my change in momentum of specifically block 2, right? Not of the whole system. Remember, the momentum doesn't change in the whole system. It's specifically the change in block 2, right? Okay. So then when I plug this in, I'm going to now have to do the actual calculus part of this, where I know that the change in momentum is equal to the integral of the force function F max times sine of AT dt from 0 to t sub c. Oh, and I probably should plug in this right here. 18/7 mv naught equals, oh, and by the way, I can take the F max out of there. Okay. 0 t sub c times sine AT dt. Okay. The integral of, and if you ever forget, and I'm so bad about remembering the integrals of the integrals and derivatives of trig functions. I'm especially sine and cosine. I'm really bad at that. But they do give it to you right here. The integral of sine of there's a sine of ax, right? Is going to be -1/a cosine ax. So this is going to be is going to end up looking like 18 over 7 mv naught equals F max. This is the part that was integrated. That's going to be negative 1 over capital A times cosine AT. Okay, and that has to go from 0 to T sub C. Okay. And if you remember that cosine of 0 is just 1, if you forget that, it's also on the formula sheet right here. Cosine of 0 degrees is 1. Then you'll know that the second term here is just going to be 1, and then all you have to really worry about is the first term. So this is just going to turn into, let me draw an arrow so you don't get confused here. This is going to turn into 18 over 7 mv naught equals F max. And then in the brackets here is going to be negative 1 over capital A times the cosine of capital A T sub C. Then you have to subtract it from the 1, but it's going to be negative, right? Sorry, subtract it from the second term, which is this 1 over A, negative 1 over A times 1, so it's just 1 over A. Negative of a negative is positive, so it becomes plus 1 over A. Okay. And then all you have to do is divide this whole part in brackets on both sides, and you get your expression for F max. Okay. This is going to be 18 mv naught over 7 times negative 1 over A cosine A T sub C plus 1 over A. Okay. And that's like really, really ugly, but you can leave it like that, and you can actually simplify it a little bit more if you wanted to. I don't want to simplify it anymore, and that actually does fit what I've got, because I've got M, V naught, A, and T sub C, and there's nothing else in it, right? So this is technically a full credit. This should be a full credit response for that question. That's on there. Okay, that should be the full credit response. Okay, and the second part B is, let's see, consider a new scenario where block 1 initially slides in the positive x direction with a new constant speed v1. Block 2 initially slides in the negative x direction with constant speed v naught. Blocks collide and stick together in the new scenario. The two-block system has constant speed v naught after the collision. Derive an expression for v1 in terms of v naught. Begin your derivation by writing a fundamental physics principle. Okay. And that's actually not that bad because this is just conservation of momentum, right? So you've got the block 1 was just 1m, so it's m v1 minus 6m v naught, okay? And minus because it's negative, and set that equal to, again, they stick together, so it's 7m, and they move with v naught. Okay? And all you have to do is you've got an m in every single term here, right? So you end up getting v1 minus 6 v naught. So v1 minus 6 v naught equals 7 v naught. And just solve for v1. So add 6 v naught on both sides, and you get v1 is equal to 13 times v naught. So that is your expression for that. Okay? That's all you have to do. It's a simple conservation of momentum problem. That's all it is. Okay, don't think too hard about it, because you'll might mess that up. Okay. Okay. Question number 2 is these two springs attached to two different sides of a block. Spring B has more spring constant than A. It actually has double the spring constant of A, and then each spring is at relaxed length. In figure 1. In figure 2, we move the block to position x1 as shown, and we hold it at rest, and then in the next part we'll let it go. Okay. One thing to keep in mind, right, is, and this is very, very important, and this will get people tripped up a lot, is if you take the block, right, and it doesn't matter if you scoot it to x1, right, you're stretching A past its equilibrium length, and you're compressing B below its equilibrium length. You're actually doing the same thing to both springs, right? You're actually doing the exact same thing to both springs, okay? You're stretching A, you're compressing B, but you're actually stretching and compressing them by the same distances, right? Assuming that the block is at the point where the two are at equilibrium, right? So you're actually doing the exact same thing to both of them. So you actually can just plug in for spring potential energy 1/2 kx 1/2 k sub sorry 1/2 k x sub 1 squared, right? Because you're actually doing the exact same thing to both of them. Stretching the spring to x1 is identical to stretching it to is identical to compressing it to x1. Okay. Energy bar chart can be used to represent the potential energy of spring A, potential energy of B, and kinetic energy. Okay, so if I'm doing this, right, um, I've already established that A and B are being stretched or compressed the same distance. Okay. So that means that their potential energy, right? The potential energy of A is just going to be 1/2 k x sub 1 squared, but the potential energy of B is going to be 1/2. It's actually 2 times k because it has a double the spring constant of A, x sub 1 squared. So you'll notice here that this is actually going to be that B actually has double the potential energy as A, right? So it doesn't matter how high up I draw these, I need to represent that B has double the potential as A, right? So let's see, 1, 2, 3, 4, 5. I'm going to draw 4 on B. So let's see, 1, 2, 3, 4. Okay. And then A is going to get only 2 because it's half as much, right? This is as it passes, wait, this is at x equals x1. X sub 1 is the not equilibrium, sorry, is the amplitude. And at the amplitude, all your energy should be potential. It shouldn't have any kinetic energy starting out. So this should actually just be a clear 0. And it says indicate that with a distinct line on the 0 energy line. So boom, no energy there. Should never go negative. Okay, shouldn't ever go negative. You only ever really see negative energy in potential energy functions because they're weird. Okay. Okay. The block is released from rest at x equals x1 and begins to oscillate. Derive an expression for the speed via the block as the block passes through 1/2 x1. Okay. Express your answer in terms of m, k, x1, and physical constants is appropriate. Okay. I'm going to use conservation of energy, right? If this is it says there is no friction. If this is an oscillation, then the friction should be completely, or not friction, sorry, the energy should be completely conserved, right? So I'm going to say that my initial energy when I start out, right? When I start out, I've only got spring potential, right? So I've got 1/2 kx1 squared. This is spring A, okay, plus 1/2 2k x squared, x sub 1, sorry, squared. And this is for spring B, okay? Now, I do actually need to combine these, so knock those out, right? And I get 1/2 kx x sub 1 squared. I get 1/2 x, 1/2 kx sub 1 squared plus 1/2 plus kx sub 1 squared, right? And that ends up being 3 halves. It should be 3 halves. Kx sub 1 squared. Okay. And then, okay, now I'm going to also figure out what the final energy in the system should be. Because again, by conservation of energy, the initial energy should be equal to the final energy, right? The final energy, when I say final energy, I'm talking about the energy at x sub 1, or at 1/2 x sub 1, right? So I'll have 1/2 k 1/2 x sub 1 squared plus 1/2 2k times 1/2 x sub 1 squared plus 1/2 m v squared. Okay. Okay. And again, these are going to cancel out right here. It's going to look really, this kind of looks kind of ugly. It's going to be 1/2 k times this part needs to be squared, so this is going to be 1/4. That comes out and gives me 1/8. 1/8 k x sub 1 squared, okay? This part right here ends up being k times, this is going to be 1/4, so it's going to be plus 1/4 k x sub 1 squared, okay? And then this is just going to be 1/2 mv squared, okay? And then right here, I actually need to combine these two, and I can do that by creating common denominator on these two fractions, right? I can turn 1/4 into 2/8 and then combine it to give myself 3/8. So this would become 3/8 kx sub 1 squared plus 1/2 mv squared. Okay, that's the final energy. Now I just got to set the initial energy equal to the final energy. So the initial is 3/2 kx sub 1 squared equals 3/8 kx sub 1 squared plus 1/2 mv squared. And I'm going to do something kind of crazy here. Okay, I'm going to do something kind of crazy. I was thinking about it and I was like, I think this can work, right? I can actually factor out my 1/2s here, right? I can actually knock out some 1/2s here. I got a 1/2 in everything. Okay, and I can actually do that, right? So this is going to now become 3kx sub 1 squared equals 3/4 k times x sub 1 squared plus mv squared. Oh, wait a minute. Now this is really easy to take care of, because if I subtract this 3/4 kx squared on both sides, I can actually really easily subtract that from 3kx sub 1 squared. So this ends up being, so this becomes 3kx sub 1 squared minus 3/4 kx sub 1 squared. That ends up being 9/4. It should be 9/4 kx sub 1 squared. So it should be 9/4 kx sub 1 squared equals mv squared. And all you gotta do now is divide m and then root both sides. So I'm gonna skip those steps really quickly just to show you that it should end up being 9kx sub 1 squared over 4m, and then you square root. Okay. That's not that bad, right? You can simplify this more if you wanted to. You could technically pull the 9, the 4, and the x sub 1 out and turn it into 3/2. 3/2 times x sub 1 times root k over m, if you wanted to. I don't really care to, right? You're just trying to get through this as fast as possible, right? You can technically factor it out if you want to, but you don't have to. Okay, and you should still get full credit for that. Okay, this part is a little confusing. This is a damped oscillation because it says that it shows this is what the position of the block is as a function of time t. And then it mentions, it actually throws you off because it throws in a little blurb right here that says that the block spring system is placed on a new surface that does have friction. Okay, which means that the oscillation is going to look the exact same, except that your kinetic energy is going to be dissipated as you go through, right? So what I'm going to say is that, first off, notice on the graph, anywhere where where the slope is 0 means that kinetic energy should be 0, right? So anywhere where the slope is 0, kinetic energy has to be equal to 0. So that's going to be right here, right here. That's going to be, right there, right here. Basically, at any of these numbered, these labeled points, the kinetic energy has to be 0. Okay? Each of these points, the kinetic energy has to be 0. So I'm going to say Ke equal to 0, right, at each of these points. So that means that at the beginning it should be 0, and then it should hit a maximum in between the points, right? It should hit maximum in between the points. So it should be 0 at all of these right here. 0, 0, 0, 0, 0, 0, 0. Okay. And it has the same period, right, before coming to rest. Okay, so what's going to happen is it should hit a maximum up here. It's going to kind of look, okay, there's my maximum right there. And what's going to happen is it will never reach that maximum ever again, and it'll keep decreasing until eventually it hits 0. So it'll go up like that, and then it'll go. I drew that one a little probably too high, right? But it'll go up, and then up, maybe not so much, and then it'll just kind of die out. Okay. This is probably not perfect. I probably should have made it go a little bit lower than that, but then it kind of just ends up being like really pathetic towards the end, and eventually it'll stop, right? So the kinetic energy should start out pretty high, and then it'll kind of, do you notice how it's kind of trending downwards as it goes, right? It should decrease. The maximums need to decrease in the kinetic energy because it's being damped, right, by the friction. Okay. The block is replaced with a new block of larger mass. The coefficient of kinetic friction is the same. The new block is moved to the same position, released from rest. The kinetic energy is function of time. What would change in the graph from what I already drew? What I'm going to say right now is more mass. More mass means more work done by friction. Okay. If work done by friction increases, then block stops sooner. Okay. This is, and I guess you could argue this too, is that the work done by friction is equal to mu mg times the distance, right? And increase mass, increase mass, increase work done by friction. Okay. So you increase the mass, then more work is being done by friction. That energy is dissipating faster. I should probably also note that too. Energy dissipates faster, or sooner, you can say. Maybe it dissipates maybe not faster. Well, I guess a little bit faster, but energy dissipates sooner, right? Because technically more friction force is acting upon the block, right? That was the way I first rationalized it in my head. This looks like a pendulum problem, but it's actually not. It's actually a energy problem. Okay. We did energy with an oscillator in the previous one, but now we're doing energy with not even really a pendulum. This is actually your experimental design question. A box is connected to one end of a rigid rod, so you have a box in this little, a block in this little box, and then you have it connected to a rod. It's a rigid rod, and then you let it go from some height. It hits the stopper, and the whole box rod system stops moving, and then the block can actually continue and slide out. Okay. And it keeps sliding out, and it slides on the surface, which has no friction, right, or negligible friction. Students are asked to experimentally determine the acceleration due to gravity g using a linear graph. To determine g, the students are permitted to use measurements only from a meter stick and a motion sensor. So I can't bring anything else to the party. I have to use the meter stick and the motion sensor. Okay. Okay, so here's what I'm thinking, right? I lifted the box up to some height. This is the easiest thing to think of is conservation of energy, right? If I know that, like, up here, right, I'm going to have mgh, and it's all going to turn into 1/2 mv squared, then I can use a meter stick to get the height, and then I can use the motion sensor to get the velocity, right? And then I can actually solve for g from there, right? So I'm going to say for part A, I'm going to raise I'm going to say block system to a measured height h. Okay. I guess I should probably say measured with meter stick. Okay. Release and use motion sensor to record the velocity of the block after leaving the box. Okay. Okay, I stated my 2 pieces of equipment. I said what I'm going to do with them. Now I need to address experimental uncertainty. So I'm going to say, let's see, release and use motion sensor to record velocity of block after leaving the box. Repeat for 5 current heights. Okay. For 5 different heights. Okay, so if we lift the block the block up, we're going to lift it up different heights each time. Okay. Okay, and then my procedure for part B, or then part B is going to ask me about how can I graph the data and how is that graph going to be analyzed to determine the value of G. Well, the way to do that, right, is I can use my conservation of energy. mgh is equal to 1/2 mv squared. I notice right off the bat my m's cancel out, as typically does in conservation of energy, and this becomes gh equals 1/2 v squared. Gh equals 1/2 v squared, and I need to get g by itself, right? So I divide h on both sides, and that just becomes g is equal to v squared over 2h. And wait a minute, I've effectively linearized the equation, right? This right here is my rise, this right here is my run. So I would say graph v squared on the y-axis and 2h on the x-axis. Slope of line of best fit gives G. Okay. I think what you can do actually is you can actually move the 2 over, and it should give you about the same thing. If I'm not mistaken, I think it gives you the exact same thing, because I think you can scale it by some value and it still works. If I remember correctly, it should be. So you can actually do this as well. You can move the 2 to the other side, and this becomes 2g equals v squared over h, and then you can say graph v squared on y-axis, h on x-axis, slope of the line divided by 2 gives you g. Okay. That's one way to do it. Experiment's repeated, but now there is rough friction. Okay, there's friction here, right? They give you a coefficient of friction, which is mu. The block box system is pulled aside so that the center of mass of the block is displaced various vertical distances h and released from rest. For each vertical distance, the students measure the position h max at which the block comes to rest. Okay, so I guess they lost their motion sensor. Maybe they were playing around with it too much and they got their motion sensor privileges revoked. Okay, so indicate 2 quantities, either measured quantities from table 1 or additional calculated quantities that could be graphed to produce a straight line that could be used to determine mu. Well, what I'm thinking right now, right, is that this system is mounted right up here and it has mgh, right? Then down here it's immediately all 1/2 mv squared, and then here it's all been dissipated, so it's all force of friction times the distance, right? So I'm going to use conservation of energy to solve this problem because it's the easiest way to do it, right? I can actually cut out the middleman, the 1/2 mv squared, because I'm not measuring velocity, right? I'm not even measuring mass. So I can do mgh equals the force of friction times x max, right? Well, force of friction, I know, is mu times mg, right? So I can do mgh equals mu mgx max, and wouldn't you look at that? You've got mg on both sides, right? So I can cancel those out, I can knock those out, and I get h equals mu x max. Wait, H equals mu x max. I just got to divide x max on both sides, and I get mu is equal to h over x max. That's it, right? Hey, that straight up is a linearized equation, right? So if you literally graph h and x max, doesn't matter if it's on vertical or horizontal, you could switch the two and still get full credit, then you will get mu. Okay, that's all you had to do. Okay, all you had to do is recognize this part right here. H versus x max gives you mu. Okay, create a graph of the quantities. Okay, so let me quickly. This is probably going to take the longest time to do on the video. Okay, my heights range all the way up to 0.9. I think actually I'm just going to make it, depending on how many squares I have, I might just go by 0.1. Oh, I've got more than 10 squares here. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so this is 30 by 30. Let me actually write that down so that Okay, let me write that down because I don't want to mess that up. Okay, this is a 30 by 30 grid. Oh my gosh, this is a lot. I definitely want H on the vertical axis, so I'm going to say H in meters, I think is what it said. It was in meters. And then this down here is X max, also in meters. I just realized you can actually make a unit argument for this too. Coefficient of friction has no units, and H over X max, the result of that is meters over meters, which is nothing, which is no units, right? So I just realized you could use a unit argument with that too. If I'm now thinking about it, you actually get, yeah, it kind of works out that way. That's kind of one way to. I don't know how many people would actually think that, but it is kind of good to think about. I'm not going to label every single. I don't think I need to label every single square here. I just need something that takes up about half the space. So if I actually use skip ones, I can do point. I can I'll only have 15 lines to worry about, and I go up to 90. Does actually, now that I think about it, 15 should divide easily into 90, right? I'm thinking about this. Let me see. 90 divided by 15. So if I go by point, I'd have to go by 0.06 if I wanted to use every other line, which I can do. I'm fine with that. Okay. I can do 0.06. Though I'm really bad at my sixes. Also, my first one isn't until 0.30, so maybe I should consider using a larger scale. Do you think maybe I can do? Oh, I can do 0.05. I think 0.05 would be good, right? Can I do that? 0.05, 0.10, 0.15, 0.20, 0.25, 0.30. I'm not going to make it. I'm not going to make it. I don't think. I'm not going to make it with this scale because I've only got up to here and I'm at 0.3. So, right? 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. I'm not even going to fit all the data on there, so I actually need to change the scale. I guess I probably did need to do 0.06, and I don't have my whiteout with me, so that's unfortunate. I guess I do need to do 0.06. Okay, don't laugh at me. My sixes are atrocious. Is there actually a better? I'm gonna think about this. There's got to be a better scale that I can use here. Because they are all separated by 15 by 0.15, and I can't just go by 0.5. I'm thinking I should be able to go by fives, right? Actually, if I just do everything 5, right? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. Kind of cuts it close. Kind of cuts it close. I think I can do it. That's fine. Okay, so this would say 0.05. This is going to be 0.10, 0.15, 0.20, 0.25, 0.30. Oh, 0.35, 0.40, 0.45, 0.50. That's not going to take up over half the graph space. This is a terrible graph. Why'd they give me 30 freaking squares? There's no reason. There's no universe in where 30 squares is ever going to be acceptable. 55, 0.60, 0.65, 0.70, 0.75, 0.80, 0.85, 0.90, 0.95, 1.00. And I don't need to label any more than that. That actually does take up over, that takes up over half the graph space. Technically, it does. It takes up half the graph space. It does. It does. Okay. Don't at me. My x values, they span up to 2.3. So if I actually go in increments of 0.1, I can actually do that. Oh, I shouldn't have labeled everything. I should have just done every 0.1 here. I'm stupid. If I go in increments of 0.1, so I'm just gonna label um, 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, 1.6, 1.8, 2.0, 2.2, 2.4, 2.6, 2.8, and 3.0. Okay, I think okay, I didn't have to go that far, but that's fine. I did. Okay, now I have to do 0.3, 0.76. Okay, 0.3 and 0.76 is right about there. Okay, yes, that's about it. 0.45 to 1.1. Okay, to 1.1 is right in this line right here. It was 0.45, so it's right there. Okay. 0.6 to 1.4, 1.4, and it was 0.6, so okay. And then 0.75, or so 0.75 to 1.9. That's right there, 1.9, and then 0.75. And then 0.9 to 2.3. Okay, so 0.9 to 2.3. Okay, and then you have to draw the line of best fit. You're supposed to use a ruler for this. So you can draw your line of best fit. That looks about right. Let's do that. That looks about right. Okay. Looks like a good line of best fit. Now, then it says use the line of best fit to calculate an experimental value for mu. We already said that the slope of the line of best fit is going to be mu. So all I need to do is pick beautiful points on this line of best fit to take the slope with regards to. Let's see, does it intersect? It's got to intersect at some good point anyway. Ooh, it intersects. I'm going to take this point right here. This is going to be. I'm going to take that point right there, which is going to be, let me just write my coordinates off here to the side, 1.0, comma, 0.4. And then my other one is going to be, oh, right there is another good one right there. That's going to be 1.5, comma, where does it go to? 0.6. Okay. And then all I got to do is find that the slope is the change in y over the change in x, right? Change in y over the change in x, right? And that's going to give me the change in y is 0.6 minus 0.4 over 1.5 minus 1.0. Oh, and I actually probably can solve this without using a calc, short for calculator. Uh, and that's going to be 0.5, 0.2, that's 2/5, which is going to be 0.4. Okay, I got about 0.4 for the coefficient of friction. And I don't know if that's the right answer or not because they haven't released the scoring guidelines yet, but I can at least tell it this is reasonable because it's less than 1, right? It's less than 1, so it's reasonable. Okay, that's all it is. That's all you have to do for that part. Okay, the last question is a rotation question dealing with a disk and a ring, each of mass m and radius r. They roll without slipping along a horizontal surface as shown in figure 1. The outer edges of the disk and the ring are made of the same material. The center of mass of the disk and the center of mass of the ring each initially move at the same constant speed v. The disk and the ring both then smoothly transition to a ramp that is inclined at an angle theta above the horizontal. Both the disk and the ring continue to roll without slipping as they move up the ramp as shown in figure 2. The ring travels a greater distance along the ramp than the disk travels before each momentarily comes to rest. Okay. So let's see. When you have them going up the incline, right? When you have them going up the incline, even though this is technically a rotation problem, I actually think it's easier to think of it in terms of linear kinematics. So, or in terms of just typical like Newton's translational kinematics, right? If you think about the forces that are acting on each of them, right? They're going to have normal force coming out of the plane, right? They're going to have gravitational force acting straight down, mg, and then they're going to have frictional force. Now, the frictional force has to slow down because they're initially rotating this way, right? They're initially rotating clockwise. The frictional force is going to slow it down, so the frictional force is actually going to act up the incline. Okay. And then, of course, if you were to look at the components, right, you would have a component of mg going into the plane and then a component going down, right? So ultimately, that component that's going down, right, is going to be mg sine theta, right? The normal force and that other component mg, they're going to cancel out. It doesn't even really matter, right? So the question now is a matter of which friction is greater, right? Is the friction on the disk greater than the ring or vice versa, or are they equal, right? You might be tempted to say equal because you're thinking they're made of the same material, they've got the same mass, so their coefficients, or so their friction should resolve to be the same. However, that's not the case because the disk does not go up as far, and also just keep in mind that the coefficient, that the static friction, when you solve for static friction, it can, when you solve for the value, it's the maximum value. It can be less than that though too, okay? So it can be less than that too. So keep that in mind, right? That's going to come back, I think, later, right? So which one's greater? Which one's less? Well, think about it. If the disk momentarily stops first, then that means that it had to have a greater acceleration acting on it to slow it down faster, right? So I'm going to say that the disk had to have more friction acting on it, okay, than the ring, because the net force for either object is mg sine theta minus the force of friction. Okay. If the if the what am I trying to say here? If the object stops first, okay, then its acceleration is, or deceleration, sorry, is greater. So the force of friction on that object must be greater. Okay? If you think about it like this, that when it gets on the ramp, it has a negative net acceleration because it's slowing down, right? It's decelerating. Then what happens is your friction force is going to be greater than the mg sine theta. It's just a matter of which one's going to be stronger, right? That's my justification right there. Part B asks you to do a little bit of derivation, and I'll do it down here at the bottom. It asks us to find, if you got a cylinder, has mass m, radius r, rotational inertia I about central axis. The cylinder rolls up without slipping, inclined at an angle theta above the horizontal. Derive an expression for the static frictional force F exerted on the cylinder by the ramp. Express your answer in terms of m, r, I, and theta and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle. Yeah, okay. We've seen that like a bajillion times. Same old song and dance, okay? I'm just going to do that little derivation down here. I'm going to do... I remember solving this a little bit before the test. It was... you have to write both Newton's second laws. So I'm going to write F equals ma, F net equals ma, and then I'm going to write torque net is equal to I alpha. Okay. Okay. So now when I calculate these things out, I'm going to actually start by setting these things up. The net force, again, we said was mg sine theta minus the force of friction, which, by the way, I don't actually have to solve for it because it just wants me to give, it just calls, it says call it a, lowercase f, okay, equals ma. The net torque, right, the only thing that's actually causing a torque on the object is friction. So I'm going to say R times the friction is equal to I alpha, okay? I want to recognize this too, that alpha is equal to A over R, and we've done this like a bajillion times. Maybe we did it a bajillion times. Maybe think we did it a bunch in Physics 1. So I can actually substitute RF equals I times A over capital R. And then I need to get A by itself, so I can actually plug it into here. So this becomes, I divide both sides by R, multiply both sides by, divide both sides by R, multiply R on both, capital R on both sides, and I should end up getting that acceleration is equal to R squared F over I. And that's all I have to do. I just plug that into here. Okay? And when I plug that into there, I get mg sine theta minus force, or friction, equals R squared friction over I. Now I need to get F by itself, right? So I'm actually going to move this F to the other side, and this is going to give me mg sine theta equals R squared F over I times, plus F. Okay, and I can factor out my F now to turn two F's into one, right? Mg sine theta equals F times R squared over I plus 1. Okay? And all I have to do now is divide this on both sides, this part in the parentheses on both sides, and I should get that the force of friction is equal to mg sine theta over capital R squared over I plus 1. Okay, and I don't need to simplify that any more than I already have. Okay, I actually don't want to simplify it. I think you could technically pull, like, somehow, some way, pull the I out of it. You could. It'd just be really dumb to do that. So I'm going to leave it like this. And this technically fits the parameters of the problem. It said, what was it? M, R, I, and theta. Okay, well, I've got M, I've got R, I don't have, there's theta, sorry. And then I is right there, right? And then I've got my fundamental constant G right there, so that's perfectly fine. Okay. The final part says, in a different scenario, the centers of the mass of the original disk and ring each have the same initial speed v as they did in the original scenario. The ramp is replaced by a new ramp on which the disk and the ring initially slip as they roll up the new ramp. That means that kinetic friction is acting. Okay. Is the magnitude of kinetic friction force exerted on the disk by the ramp greater than, less than, or equal to the magnetic magnitude of the kinetic force exerted on the ring while both are slipping? This is important to note that kinetic energy can only be one value, right? We don't have that less than or equal to thing. Kinetic energy can only be one value, right? So in this case, they should actually be they should actually be identical. Okay, um, the frictions should be equal. Okay, um, because um, because what was I going to say? Because um, 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 totally blanking right now. What was I going to say? Um, oh, sorry. Because kinetic friction does not vary, and both objects are made of same material, so same mu, okay, and have the same mass, okay? So because friction only depends on the coefficient and the mass, then this is going to be, because the friction only depends on the coefficient and the mass, that is going to be, um, um, it should be the exact same, right? They have the same mass, they're made of the same material, so same coefficient, all that fun stuff. Okay. Okay, that is the end of the Physics C Mechanics FRQs. Um, Pretty cool. I'll probably be back. Let's hope maybe tomorrow I can do maybe the Physics C EMAG stuff. So yeah, Gaslight, Girl Boss, Gatekeep. Have fun.